Hold on, Audia. Right, so the first thing we need to remember in radioactivity, we have three radioactive elements. What are they? Right, the three radioactive elements are alpha, beta, gamma. What is alpha again? Right, sorry. Kyra now joining. All right. Excuse me, you watch your pistol. You're taking up my WhatsApp. Right? Alpha is what? A 4-2 helium particle. Beta is an electron. Gamma is just pure energy. Everybody okay with that, right? Remember that. Remember, we have to know how they all behave in different materials, what is stuck by, and so on, right? So while we're here, what is alpha stuck by? By paper, right? By a sheet of paper. What about paper? Aluminum, a few centimeters of aluminum, right? And what is gamma stuck by? By lead, right? Right? A few centimeters of lead or a few inches of lead. Right? Paper. So alpha, right? How far will alpha travel in air? No. Alpha does travel a few centimeters, right? Right? Beta is travel a few what? And gamma will travel a few kilometers. Right? If I were to give you an alpha, beta, and gamma particle, and I place them in an electric field, where would the alpha go? Beta will go, and gamma will go. Right. Kepanchu, why is the beta traveling on a shorter path than the alpha? Beta,
No, because it lights us.
Because it lights.
Attraction is strong on it.
Right. And suppose you have a magnetic field now. What does X mean again? What does X mean again? Magnetic field going in or out? So magnetic field going in. All right, what is here? Nalia, could you figure out what direction the alpha particle will move in? What law you will use? Fleming's Neptune law. So, Nalia, we go faster. What direction the force will be in? Huh? So magnetic field going inwards, positive particle, alpha is positive, right? So alpha going this way. So therefore it will go upwards. Beta will go how? Beta will go down, gamma will go straight through. Nice. So we need to remember those small things, right? Everybody okay with that? Shavish. Suppose we have this here Shavish. Shavish SB, like make up a particle named Shavish, right? 102. What you'll get out of let's see, you might get 51. Yeah. Right, Shavish. Suppose you are this particle, right? You are that particle. And you undergo alpha decay. What will happen? You would lose how much? What you would lose actually? you would lose a alpha particle, right? 4-2. That's okay? You lose an alpha particle 4-2, and you will become something that is 4 less here, 98, 2 less here, which is 49. So let's say it became NB, right? D, yeah, D, right? What is the police on? Wait, where am oh, sorry. You all okay with that? All right, everybody okay with that? Antonio, I'm Nikolai.
Yes, sir.
Right. So if something loses the alpha particle, it uses up 4-2 mass number, atomic number, right? But what would happen to Kayla? Suppose it lost suppose instead the same particle loses beta. What is happen? It would be what? It was an electron, right? Which is 0 minus 1, and it became what? What's the new mass number? 52, ma'am. Right? The atomic number goes up by 1, right? Right? So let's call it EL, wherever that is, right? Okay. All right. So that's just some small things that you need to remember about particles. Right, Sean? All right. While we're here, I'll even know the half-life part again. That's a new thing, right? So let's take a look at some from everything else compiled, right? So Vanaya, whenever reactants, right? Whenever reactants undergo some kind of reaction, they will form products, right? What is normally formed during these reactions? Or used or given up or given out? Energy, right? Anybody remember the energy mass relationship? Right? So there is a relationship that says that E is equal to the change in mass by the speed of light squared. Right? The change in mass is the mass of the reactants minus the mass of the products. Their masses are not the same. Although the atomic numbers and things normally add up on mass numbers, their masses are not the same. Right? And because of the difference in mass, right? By the speed of light squared, that's if you were to multiply these two, it gives you an idea of the amount of energy that will be released during this reaction. Okay, so the energy released during these reactions is given by this. Delta M is the change in mass from reactants to products, and C is the what again? Speed of light, right? 3 by 10 to the 8. Okay with that? So you need to remember that because you will see this in a keep question. Same thing. Why? Why? Yeah. I thought that was last year. They told you one. Oh yeah, copy it down. Let's move on. The same calculation. I'll do one just now, right? Alright, so those are the things that I need to remember from compound, right? Right. What we want to take a look at now is the form 6 part of it.
Is equal to
Right? And before we do that, right? The higher what you will recognize is that the higher this energy per nucleon, the more stable the atom is. If you look at the notes, right, there's a diagram that looks something like this. Right? This diagram shows that these elements here, I went down a little too far, but these elements here are very stable. They have the highest, what we call the binding energy. That's the energy required to break the bonds of the nucleons, right? It's called binding energy, and the graph looks like this. It's in the handout. You know, don't show this one, right? But here represents the elements with the highest binding energy, right? And these are the most stable atoms called the transition metals. Okay, all of these here. All right. All right. So what I want to focus on today, we'll do a question on this shortly, because a question came exactly on this, just like form 5 would. Right? We'll do this one, but what I want to focus on is half-life. Right? I want to focus on half-life and nuclear decay. So head up radioactive decay. Head up radioactive decay. Again, if you don't want to write this, you don't have to. This is in the handout, right? That's true, yeah. Wide back. Yeah, be careful. That's somehow the other grass fights and do that. I don't know how we do it. All right. All right. So watch here. So we all know, right? We all know that radioactive elements behave like that. Are you okay with that? That's called a decay curve. So radioactive elements decay like this. And the time taken to reach half of the original amount of nuclei is called what? Half-life. Everybody remember that? So the time taken to reach the half and Norton 2 is what we call half-life. Right? So T to the half is equal to half-life. All right. So we need to develop some kind of equation now to help us work out or help us see how the nuclei behaving with time. Right? For the pure mass people, what kind of function is that? An exponential function. Right? Okay, so watch here. Right now, there's a special quantity called activity. Right? That we need to learn about. And activity right? It's measured in becquerels and is basically sort of the rate of decay of a radioactive element. right? Technically, the number is integration per second, right? Right, number of
It's in the notes, right?
nah, everything is in the notes. But I want to show you how where everything comes from, right? It's the last thing in the module. Right? It's the number of disintegrations per second. So what you see here? Are you ready? Guys, you ready? Right? So what you will see is this. You will see that the activity is equal to something called lambda. Lambda is what we call our decay constant. Right? That's the probability of a radioactive element K, right? So A is equal to lambda multiplied by N. Right? So this activity of the radioactive element is given by this decay constant by the number of nuclei in the atom at that point in time. Okay? And here's the important part. People who are not doing maths well, you have to learn this part off because the proof that you have to learn. Right? Everybody ready? Which one? Decay constant. Decay constant. Oh yeah, copy that down. I want to show you this part here. This part is important. Are you going now? Ready? All right, ready? So watch this here. You got have this, right? Sean, watch here now. Oh, you're watching down. Do I have YouTube? Are you ready? So watch this here. Everybody ready? Right. So here's what we just learned, right? We just learned that activity is lambda by N. Right? Yeah, because it's decay. Yeah, so I should have that there initially. But in this part of the proof, I want to leave it out. Minus indicate that it's decay, right? So we know that I said that activity is rate of decay of the radioactive element. Remember in rates of change, rate means dn, right? dt, right? So rate of decay represents the rate at which the number of nuclei change over time. Okay? So the rate at which the number of nuclei change over time is activity. And that is equal to lambda n. Okay? If I were to separate the variable, watch here. If I were to separate the variables, bring the n on this side, I'll get 1 on n dot dn, and bring the dt on this side, and then integrate. Here, I'll get ln n. Here, I'll get lambda t. Okay? Well, plus some constant, right? Which we could assume to be 0 for now. All right, good. Let me do assume. I will show you how to carry that. When you move the ln across, what you will get? E to the lambda t plus c, right? That's okay? So it means that n is equal to E lambda T multiplied, addition means multiply, right? E to the power C. Let's call E to the power C some random constant E. Let's call it A. Okay, all right, sorry. Let's use R. Okay, no. Let me use B. Let me use B. Oh gosh, all right. Let me use K. Like K, right? So that's KETC. Right? But watch this here. What do we know happens initially? We know that when, look at the graph, we know that when T is 0, N is equal to what? N is equal to N naught, right? So if I plug that in here, I'll get N naught is equal to K e to the power 0. Anything to the 0 is 1, so K is equal to N naught. Okay? So now the formula becomes, watch this here. I'm going to replace this. The formula becomes N is equal to N naught e to the minus lambda T. You okay with that? Yeah? Right? So non-math people, just make sure you understand here. From here to here. Yes, you gotta memorize and write. But understand from here to here. We gotta memorize. I'll find out with them. Write on your hand, it become the stick it in the book. All right? Everybody okay with that? So that is how you find, or that is how you find the relationship between number of nuclei and time. Yeah, that is good. Timothy, you okay with that? What you okay with? Huh? What? You never take us on this. I do one on this. Well, I do one on first principle. So that is that. Are you okay with that? Nalia? No, I didn't even write it down. Do you understand what's going on here? Leave it, shall talk to your father then. Right. Hatta. One time. All right, so this is the number of nuclei present after a particular time. You have an eye? Right, just watch here, last thing. Last thing that we have to understand. What has happened when N is equal to N naught and T? Sorry, N naught and 2. Half-life. Time is equal to half-life, right? That's okay? Aryan, if you can write this part out here, or tell me what to do, I'm going to pick up you. So, Aryan here, what trying to do, right? I said when N is equal to half of the original amount, that time is the half-life. I want to take this, put it in here, and find a formula for half-life. Hey, wait, where I magically put this minus sign? I'll leave out the minus sign. Yeah. Sorry. No, I was wrong. Sorry. I can't magically bring in the minus sign here. Sorry. Right. Try this pass. That's how you have to come and do it. Hurry up. Yeah. I think nobody know I don't All right, ready? Daria? Aria? Right, so Arian, what to do, right? I wanna basically get a formula for half-life. Well, I didn't ask to know the formula, I want to get it from you. What to do? Right, so if I substitute n is n naught on 2, and naught staying as it is, and I'll get minus lambda by half-life. All I'm with the n naughts. So you'll get a half is equal to e to the minus. What do I do now? Take ln on both sides. So I'll get ln of a half is equal to minus lambda and a half. Like not much people nearly up. This here is 1. Right? And you can bring the power in front of it. What is ln a half? Minus ln 2. Right? So what will happen here? The minus sign will cancel, and I'll get half-life being equal to ln 2 and lambda. Well, see that? I just leave this here and it wasn't the exact same. What is it supposed to be? So this is the formula for half-life. I'm trying to get some more jokes. I will load up on something.
So you will chat, you know.
I use that and can teach out.
So because
I know, and let's go walk around. All right. So let's do an application on this now. The other one. All right, that's now. Let's try this here, right? Again, everything in the handout in the same order and everything. Yes, you think all of them. Yeah. All right, let's try this. Online, you'll see anything? Oh, wait. Online, you'll see the screen? No, just this part alone. All right, yeah, okay. So let's take a look at part E, part C. If you can ignore, actually no. Do B and C. Ignore the first part, that's from 5 work. So Raya. Hurry up, we're doing A, B, and C. I'm opening copy.
It's the last one I asked to pick up data. So you like that? You like that? Have you had it in yet? Are you discriminating?
Oh yeah, we're going up in.
Yeah, but I'm. I can't get those to this time after the big crowd and being huge crowd.
I know. What's the problem? Well, I asked you what you yours.
Everything.
Like that.
Oh, yeah. Hold up.
No, but I think 26 and 27 because it's before the week up.
Right? I was trying to do it weekend before. On a day before, right? When I get it, I will contact them. Alright, let's go now. So 10, 10 or 10? What's the enter got? 10,000?
They said the vitamins.
Alright, let's go.
The martial arts.
I didn't get it. I don't get it. But the whole crunch was right side. Oh yeah. Let's. Y'all done? Y'all done? On the correct test. Hello?
So wait,
Yeah. PNC.
I do A. No, like
Alright, sorry. Alright, so let's go on to the calculation, right? Alright, look up here if you get lost, let me know, right? Right, we find half-life, decay constant, we okay with that? Write a formula relating them. Write the formula right here, right? The formula will be no, the party.
Yeah.
No, I said don't do it.
Party.
Party is like form one word.
So the next thing is we do.
Yeah, I didn't care what she might like.
All right, part A, the number of protons is 86. The number of neutrons is 226 minus 86. It's a neutral atom, so the electrons and the protons equal. Okay with that? Right? What is the isotope? Same what?
Masses.
Same atomic number, different. Right? And part B, that's the formula. All right, nice. So they gave us the mass of carbon, they gave us the carbon element that we're working with, and they gave us half-life. Find the number of nuclei when T is 0. How are we doing that? Soraya, how we find the number of nuclei when T is 0?
So the TV.
Yeah, the TV.
So we didn't see.
Yeah, we are on T.
So T equals 0.
Yes.
One top, but it's after equal 11 on the topic. So one, that is equal to 1.66 by 10 to the minus 24. But then if you move 11 by 1.66 by 10 to the minus 24, you get 1.83 by 10 to the minus 23. And then 2.50 by 10 to the minus 6, 1.83 by 10 to the minus 2. And you get 1.91 by 10 to the minus 6.
I don't know what you guys say there, but here's what we know, right? Right? What we know is we know that for carbon, 11 grams equal to how much?
Equal to 0.011 kilograms.
Okay, how much right? How much moles? 1 mole, right? 11 grams is like the RMM, 1 mole, which is they want to know number of nuclei. So number of nuclei is what? And 1 mole will be 6 point, in physics we use 6.02 by 10 to the 23. So that's 11 grams. How many grams are we interested in? 3.5 micro, right? So 3.5 micrograms will be 6.02 by 10 to the 23 multiplied by, divide by 11 multiplied by 3.5 by 10 to the minus 6. Okay, the divide by 11, that'll be 1 gram, and then multiply by 3.5 by 10 to the minus 6. Have a guys.
Okay.
Say, no,
Yeah, but I forgot.
so if you mark up was like 40, right? Then 44 kilograms are equal to 8 grams constant.
Yeah, I just knew that's the avocado.
And you have more than top is equal to 1.
How much is that? 1.92 by 10 to the 70. So that's the number of nuclei, right? Vinaya, how am I going to get the decay constant? Look at the question and see what they give you. The question given the mass, the particle, and the half-life. How are you going to get the decay constant lambda? Lambda is what? Is the right? How you getting lambda? Look at the formula you have in 5P. That will help you.
Oh.
5P, so you have one formula inside. right? So it will be ln 2.5 half-life. Are you okay with that? So to get the decay constant, you have to make lambda the subject, right? So Nalia, how we getting activity when t is 0? Oh, there's one thing I forgot to mention here. This formula can also work for activity, sorry,
And mass.
and mass here. So number of nuclei, it behaves the same way, the graph is the same way. Activity, the graph is the same way. Mass, same way. Okay, I forgot to mention that. Yeah, so Nalia, wait, no, what we call that now? Who? No, when I was part 2. Right, we'll work out half-life some more. Sorry, work out lambda some more again.
Very good, but that's not second.
Yes, sir.
Sure.
No,
You can
you can do whatever you.
I see.
Well done. Yep, you have to work in seconds. Right? We all got for lambda.
5.67 by 10
5.67 by 10 to the minus 4. Yeah, look. It will one it block. Right? By its final activity.
A is equal to
Right.
naught.
Right? You can write that. So you can use that, or you can use this version here. Yes. Which one? Yeah, but you need n naught. To find activity, which is A, when t is 0, you have to find it when n is 0. No, that's general, that's anything. Look at root here for you. Same formula. Same formula. Look at root there for you. No, what I say, right? To find the activity when time is 0, it's technically A is 0. So to find A is 0, it's lambda by n naught. N 0. Not n people. N naught. Let me say n naught. This n value here is this n value here. So if you want to find the activity initially, you need lambda by number of nuclei initially. So when I say N naught, that's what I mean. You want to find this. So to find that, you multiply lambda by that. That is the original value that you have in part one. That's all. So yes, you can use this formula as well, but you can't because you don't know N naught. A naught. Yeah. And over what? All right. Yeah. Yeah, mom, it's the same thing. Right? So in order for you to find the activity, you're multiplying your part two by your part one, technically. You realize that? Part one by part two?
Yeah.
Okay. And why else? Why else? How are you doing part four? All right, good. While you're figuring it out, your mother's out now. How are we going to find part four? Anybody have part three?
So that's 6 hours or 8.
That one.
That's 6 or 8 hours.
What shall got in part three?
1.09 by 10 to the power of 4.
Anybody else? You have a point? And for the SI unit?
Becquerels.
And part four, activity of the carbon 11 after 8. Yeah, why else? How are you finding that? After 11 hours, after 8 hours. Yep, because which one is that? A is equal to AO, E to the minus lambda T. What is A naught? A naught is what? Part 3. What is lambda? Part 2 and T is what? No, T is 8 hours. So you have to convert to. We're trying to find them. Copy it down.
Because it's super very clean. And everything of yeah.
Right, please remember, E is not, E is a function, right?
I didn't watch it. I didn't think that was I was so sure.
What kind of what time again? 8 hours by 60 by 6. Would A value be would A value be more than 1.09 by 10 to the 14 or less? Yeah. So what you got? 1 point.
Again, matter.
I get people want to want to conquer heroes. People are six.
What you got is power 6. How much you got? 8 points. Eight point eight by 10 to the 6. Right, Ariane, that's 8.82 by 10 to the power 6.
Again, matter. This is not right.
Yes, sir. Let's go again. Meaning what? Like instead of using 1 point. Once you use whatever you have in the other part. All right, let's go again. Next one.
That's right.
Try this there. Next one. Last one. Hold on. I have a harder one. Hold on. No, this one. Yeah, the next one is a capacitor question. You probably remember that. You all recognize this graph is like a capacitor, this charger.
Yeah.
All right, there's a question that relates. Oh yeah, last one. Huh? Somebody say for the who's doing for me. Yeah, you can do one. I'll be waiting. Have someone come for it. Yeah, it's not a curve. Huh? That's one.
Yeah, but you know what do you think of it?
No, I want to look at how it tempted.
You can like. Yeah, where we should go on.
Yeah, but he go on do 2 days, so let's see.
Two full day. Other people physics. Okay, you give us physics, right? Every Friday, school. Well, the physics up, then you can pass.
Yeah. All right, done? Do this.
Nice at you.
Says activity.
Okay, so Raya, do something when it comes to class. You ever want to sit down next to you? You want to sit down outside, I'll give you the door. All right, good. I'll make it sit down outside for now.
I'm not gonna change my BQ.
Activity didn't beat you yet.
I want to be.
I did back well. Not just number on your client.
That way the money for I give you anybody get your phone? No, really close. Like that's how Oh, yeah. But this time they give me the active.
It's basically all time. But the time. Hey. Well, that's so. Yeah,
When it fell off the bed.
Yeah. That was the funny, bro.
So here's one. Priest says, oh boy, what's about the kids? Rabbi says, screw the kids. Priest asks, is there enough time?
Obviously, I'm kind of.
Somebody now.
So one more to be personalized.
Right, look underneath, right, they gave you a conversion from years, right? They gave you a conversion for years. 1 year is 3.15 by 10 to the 7 seconds.
Yeah, I know today. Is equal to Nana and I can. Yeah. Brilliant.
I'd rather that on the back. But now,
Find it, they give you that, like. That is equal to.
I think you know it because that's when T is 0, right? That's when T is 0.
Five then people 1 6 for that. Opening 9.
yeah.
Opening 9 then people also like a snake.
Yeah.
A lot, right?
Yeah.
Yes. Yeah, 5 plus 1 like that.
They should live stream it classes like with the camera and go on there.
Right on?
Yeah.
Fine, you ready to go?
I reached the part. 3.
You hold that?
All day to three.
Better than nothing, it's better than 0. That's 0. Okay, how are you? Do you know though? Sorry, Vikash. Show you nothing. Come see? I'll see that. I'm really like. I know that because you know the one thing that.
And while I get the.
So if we see S second, we got
I guess 620 for 987.
Actually, I don't have that. Yeah,
That's fine.
yeah, soon.
Yes. I said on one. Like this how much? Pretty part 2 here.
I get 3.3.
Alright, let's see what we got. So we know that A naught is equal to lambda N naught. N naught is equal to A naught on lambda. So that's 2.5 by 10 to the 6 all over lambda. Lambda is your half-life, right? Sorry, not your half-life, but ln 2 on your half-life. So it's ln 2 divided by 4.5 multiplied by 3.15 by 10 to the 7. What y'all got for N naught?
5.11 by 10 to 14.
Right? The activity after 9 years, so you're using A is equal to A naught e to the minus lambda t. You know what A naught is? A naught is 2.5 by 10 to the 6. Lambda is
5.
what it works out to be
4.89 by 10 to the minus.
4.89 by 10 to the minus 9. And then we multiply that by time, which is 9 years. So you multiply 9 by 3.15 by 10 to the 7. And as Aaron recognized, that's 2 half-lives. So you can just multiply by a quarter. Okay? So what you all got for A? 1 by 10 to the 6 or something? 1.28 by 10 to the 4. Huh? 1.28 by 10 to the or 14. 1 4.
Hey, you can run. You don't have to.
Yeah, because like I put up your
Yeah, pull up your calculator and screen here.
the gap.
I don't have one.
This button. So I guess
That's a good idea. Yeah.
6.5.
Right, so that's what? That is 2.5 exponent 6 multiplied by e to the power of what? Minus 4.89 exponent minus 9. Right? Yeah. So the answer was 1.28 by 10 to the 4. Y'all got those values?
So you have your own before.
Oh,
You have 2.5 when you
Oh, yeah, yeah.
A naught? You sure?
That that 5.11 is N, not the.
No. That 5.11 is N naught. A naught is this 2.5 here. Oh, sure. I guess something different.
I think you're right there.
6 point something
6.2.
by 10 to the 5. Yeah, I got it. 6.25, yeah, I got it. P Blackwell. Timothy. We'll have distracted Timothy. Timothy distracted. What would the activity be after 12 years? Same formula, right? How much you get? How much? 4.19 by 10 to the 5. Is the video clear enough? Somebody get 3.95. 3 point, you didn't do anything. 3.95. 3.95 factor. Alright, last part. What you see on non-math people, right? Huh? Right, what is last part here? Nalia, especially you. Non-math people, watch up here, right? The source cannot be disposed of until its activity is less than 100 Blackwell. For how many years must the source be retained before discarded? So the activity that you're working with now, same formula, A is equal to A naught e to the minus lambda t. You have to solve for t. Okay? And A value used is 100. And the original value was 2.5 by 10 to the 6. And then you minus in E lambda. What's lambda again? 5 point. 4.89 by 4.89 by 10 to the minus 9. Right? And then you have to solve for t. Right? So I'm just going to show you something here because non-math people might have to learn it. A is equal to A naught e to the minus lambda t. Carry across the A naught. Take ln on both sides. So you'll get minus lambda t is ln A on A naught. And then make t the subject. So t will be equal to ln A on A naught minus lambda. So that's the formula you're using to find t. Okay? So non-math people, they might have to learn it that way. Non-math people, yeah. What you get for t?
64 years.
Yeah, two. I don't work it out from my plane.
Yes, sir. We could find any numbers. We also
Finish binary numbers.
yeah.
I mean,
But yeah, if we have more binary too,
more binary will be module 2.
yeah.
We done in module 2.
Yeah, you see, we can see that, yeah. Probabilities.
Binary numbers.
Binary numbers. Binary expansion.
Binomial expansion. Alright, copy it down. Make a list of the things that I want to do. To do this, come on. Right? Make a list, right? But I want to report some of the things and do little videos for us to watch.
But there we see, right? I already board.
I will get some views for other people. Time, sir.
Wow.